Alright, so Lewis structures. This is the first model of bonding that we will consider in this chapter. I think there's going to be three, maybe four of them altogether. And this is probably the simplest one. In the Lewis, electron dot structure model, the bond is considered to occur when the atoms share electrons between the two nuclei. And the reason why they would do this is, I hope you learned in your first year chemistry course, is that they're trying to fill up that valence shell that they have. So for hydrogen, that it wants two electrons to have a full shell. Most of the other representative elements, they want to have 8 electrons to have a full shell. And so that's the reason behind all this. This is the reason why the electrons should be shared between the atoms. So the image that we have is that valence electrons will be shared, throughout the whole atom. So throughout the whole molecule. So each atom has a set of valence electrons that it kind of brings to the molecule. And then you take that total number of valence electrons and you distribute it into these bonds in the molecule. The atomic nuclei in the molecule are represented by element symbols. Single electrons will be represented by dots, and pairs of electrons are represented by dots or perhaps lines. You could just, you kind of use either way. And electrons that are shared will get placed between the nuclei, and electrons that are not shared are called lone pairs, and they will be kind of localized onto one nucleus. Now, this is kind of an art. There's kind of an art for doing Lewis structures, but there are some rules that can help guide you as you do it. The first step in this is to sum up the valence electrons for all the electrons in the molecule. In other words, what you do is you take every atom in the molecule, you determine how many valence electrons it has, and then you add up all those valence electrons together. If you have a negative ion, you will add electrons, to that total, and for positive ions, you would subtract the appropriate number of electrons. You want to keep all the atoms in the molecule connect all the atoms in the molecule with single bonds first. Before you make multiple bonds, before you try to get cute or anything like that, just make sure everything can be connected together. And this is where kind of the experience factor comes in, just kind of learning typical bonding schemes. Some things I can tell you: hydrogen will always have one and only one bond. You cannot have multiple bonds. You cannot have lone pairs. Okay, it cannot form chains either. In other words, like a hydrogen chain. There's no such thing as that. So usually the hydrogen atoms would be kind of surrounding other atoms. Oxygen will usually have two bonds, nitrogen 3 and carbon 4. There are exceptions to this, and but those are exceptions. The rule is try to keep it so that oxygen, nitrogen, and carbon has the appropriate number of bonds. After you do all this, after you have everything connected, you then fill any valence shells, what we call the octet, up with lone pairs, and I'll show you how that's done. And then we count the number of electrons shown. If we have too many electrons, then we start to form multiple bonds by erasing lone pairs, and that will reduce our number, and you'll see how that's done as well. Okay, so a couple examples here. We have C2H6, and the first thing we do is count the total number of valence electrons. Now, carbon's a group 4 element, and therefore each carbon atom has 4 valence electrons, and then we have 2 of them, so that gives us 8 valence electrons from carbon. Hydrogen is a group 1, so it's got 1 valence electron, and there's 6 of them. So plus 6 more valence electrons. So we have a total of 14 valence electrons in the whole molecule in order to to distribute around. So what we'll do is we'll connect these 2 carbons. Remember, we connect all atoms with single bonds first. So connect the 2 carbons, and then we'll have hydrogens radiating out from these carbon atoms with single bonds. And so we have a structure where we have 2 carbon atoms and we have 6 hydrogen atoms, and everything's connected with a single bond. And now what we're going to do is we check to make sure everything has an octet. And remember when we do this, that these lines between the atoms represent bonds, and as such the electrons are shared between them. So in other words, this bond counts for 2 electrons. And so those 2 electrons can be said to be surrounding hydrogen and surrounding the carbon. So any electrons in a bond count for both atoms. So when we look at hydrogen, each one of these hydrogen can be said to have 2 electrons around it because there's 1 bond to it. Each of the carbons can be seen as having 8 electrons around it because there's 1, 2, 3, 4. There's 8 electrons around each of those carbons. Okay. So everything has an octet. Now we count the total number of electrons: 2, 4, 6, 8, 10, 12, 14. So each bond counts as 2. And we have 14 electrons, which is how many we need. And so that would be the Lewis structure for C2H6. Now contrast that with C2H4. Once again, 4 times 2, so we have 8 valence electrons from the carbon. We have 4 hydrogens, which gives us 4 more valence electrons, and so that's 12 valence electrons altogether. And once again, we'll connect. We'll even out the hydrogens, and again, that's where kind of experience comes in here. There won't be 3 hydrogens on one and 1 on the other. You know, they'll try to be equalized out. And now we check for an octet, and hydrogens are fine, but the carbons, they each need 2 more electrons around them, so I'll put lone pairs to fill out those octets. And now I will count my electrons. So 2, 4, 6, 8, 10, 12, 14. I have 14 electrons shown. I only can have 12 in this whole structure. And so this is where multiple bond formation comes in. What I'm going to do is I'm going to erase those lone pairs I put on each carbon. They still need an octet though. So I'm going to put 2 electrons, I'm going to put 2 more electrons between them to make a double bond. And now if we count them, 2, 4, 6, 8, 10, and then 12 down here, we have 12 valence electrons, and so that would be an appropriate Lewis structure for C2H4. Alright, so here's a few molecules for you guys to try. Can pause the video at this point if you want to try them by yourself first, but I'll go over them and work them out for you just a sec. Okay, so we're going to use the same method for all of these. So silicon has 4 valence electrons. Chlorine, being a halogen, has 7, and there's 4 of them all together. So that'll be 28 plus 4. So 32 valence electrons. So put our silicon in the middle. Our chlorines surrounding it. Okay. Now the silicon has its octet. The chlorine needs their octet. So this is a little trick. You can use lines for lone pairs too. It goes a little bit quicker. So we'll put a lone pair around those chlorines. And if you look, we have 8, 16, 24, 32. Okay, so 8 on each on each of the 4 sides of the silicon. There's 32, and that gives us a good Lewis structure for SiCl4. For PF3, the phosphorus has 5 valence electrons because it's group 5, plus 3 times 7 from the fluorine. So that gives us 26 valence electrons. Have the phosphorus. The halogens, they tend to only form 1 bond. Usually, not all the time, but usually they only have 1 bond. So you'll put the phosphorus in the middle. You have the halogens radiate around it, and then you surround it with lone pairs to fill up the octet. And you count the total number of electrons, and each line is 2. So we would have, 8 on this side, 8 more for 16, 8 more for 24. Plus 2 is 26, and so that is a valid Lewis structure for PF3. Alright, SCl2, 6 plus 14. I'm kind of trusting you guys know where these are coming from now. 20 valence electrons, so S in the middle, Cl on either side. Fill up the octet. We have 8 on one side of the sulfur, 8 more on the other side for 16. Plus 4 from the lone pairs, which gives us 20, so that's a good structure for the SCl2. And then finally we have HCO3, so we'll have 1 plus 4 from the carbon, plus 3 times 6 from the oxygen, and then we add 1 more valence electron due to the negative charge of this polyatomic ion, this bicarbonate ion. So we have 5 plus 18 is 23, plus 1 is 24. So we have 24 valence electrons. Once again, I'll put my carbon in the middle. I'll have the oxygens radiate around it. And rather than putting the hydrogen on the carbon, I'm going to put it on one of the oxygens because that gives one of the oxygens 2 bonds. Doesn't give them all 2 bonds, but it gives one of them 2 bonds. I'm going to fill out octets with lone pairs. Okay, and then I count the total number. So I have 8 on this side of the carbon, 8 more, up here is 16, 8 more is 24, plus 2 is 26. So I have too many electrons in this. I need to get rid of some, so I'm going to form a multiple bond between a carbon and one of those oxygens that, that doesn't have the hydrogen attached to it already. Because again, we kind of want to limit oxygen to having two bonds, no more than two bonds if at all possible. So I'm going to make a double bond between those two, and then that brings my total number to 24 valence electrons. And that would be a good Lewis structure for bicarbonate. All right. So I hope this introduction to Lewis structures has helped you. In the future we'll go into resonance structures, and if you're real on top of the game, you realize that there was a resonance structure for this last one because I could have gone, made the double bond between the top oxygen and the carbon rather than the side. And it turns out that both things actually happen, and we'll get into what to do when we have things called expanded octets, and then we'll get into formal charge.